Hello everybody, I am the Math Hobo, and today we're going to be talking about Fourier Series. So that's the French mathematician, Joseph Fourier. And he pioneered work in heat, conduction, waves, and even the greenhouse effect, which is admittedly in a totally different field, but he was still a genius and he was very prolific. And today we are going to be talking about one of his many genius works, which is the Fourier Series. So what the Fourier Series does is it takes a function, f of x, and it rewrites it as the sum, as the infinite sum rather, n equals 1 to infinity of, plus some a0 initial term here, an times cosine of nx plus bn sine of nx. So you take this sigma and you apply it to this entire sum here, and what you will get is f of x is equal to a0 plus a1 cosine of x plus a2 cosine of 2x plus a3 cosine of 3x on to infinity. And then you move on to the b terms and the sine terms, and you have plus b1 times sine of x plus b2 times the sine of 2x and on to infinity. So this entire sum is what is going to approximate our initial f of x function, and it matters what f of x is, because if f of x looks like this, well, first of all, that's not really a function, and second of all, it's not approximatable by the sums of sine and cosine functions. So we need to place some restrictions on x. Specifically, we must say that f of x must be periodic, and secondly, f of x must be continuous over the interval 0 to 2 pi, and some textbooks say over the interval negative pi to pi, but it doesn't really matter. So we're going to go with 0 to 2 pi. And so once we have laid down these initial bounds, we can begin talking about how to isolate each term and determine it to determine our entire Fourier series expansion. And I will erase this here. So what we do to determine each constant coefficient is something similar to what we do when we approximate functions with the Taylor series. And in the Taylor series, you take derivatives and you approximate the function that way. This time we'll be doing something a little bit different. We'll be taking integrals, so we'll be doing the opposite. So now we take the integral from 0 to 2 pi, and we can do this because we said that f of x was continuous over 0 to 2 pi, so then it's Riemann integrable. So 0 to 2 pi f of x dx is equal to, and then we integrate this term here, integral 0 to 2 pi a0 dx plus integral 0 to 2 pi of the sum, infinite sum, n equals 1 to infinity, of an cosine of nx plus bn sine of nx. And these quotations mean that I just repeat whatever is above. So we can write this a little bit differently. We can write this because a0 is simply a constant term. The antiderivative of a0 dx will be a0x. So this entire integral will evaluate, not this entire integral, but this integral right here will evaluate to a0x taken from 0 to 2 pi, which is simply a0 2 pi minus a0 times 0, which simply equals a0 2 pi. And this is an cosine of nx plus bn sine of nx. So now we can expand this. We can rewrite this as the sum of the integrals an cosine nx from 0 to 2 pi dx plus, make my arrow a little bit shorter, plus some integral 0 to 2 pi bn sine of nx. Squeeze in a little bit dx there. So just to clarify, we can do this only because the integral of f of x plus g of x dx is equal to the integral f of x plus the integral g of x, which, when taken to more functions, becomes integral sigma fi of x dx is equal to the sum of the integrals fi of x dx. So just to clarify, that's why we can expand the integral of the sum of these functions to be the sum of the integrals of each function. So then we can proceed to evaluate each of these. So remember, we're taking this plus, so it's a0 2 pi plus this integral, which we're going to work out here. And that is equal to integral 0 to 2 pi f of x dx. So now we discuss this integral. Since an is a constant coefficient, we can simply pull the an out of the integral, and we get, and remember, for the sums, the limits are implied, n equals 1 to infinity. So sum of an, and we can even pull the an outside of the sum, but it doesn't really matter. An multiplied by the sum of the integral of from 0 to 2 pi cosine of nx dx. Now we ask ourselves, what is this equal? And that is equal to simply the integral, not the sum. Simply the integral is equal to 1 by n multiplied by the sine of nx. And we can check this right here. We can take the derivative. So we pull this out, it divides out, it becomes sine of it becomes cosine of nx, and it checks out. So 1 by n sine of nx is equal to the antiderivative of cosine of nx. So then we take this going from 0 to 2 pi, and then we get this becomes 1 by n into sine of n into 2 pi minus the sine of n into 0. And the sine of 0 is very obviously 0, so this term doesn't matter. And then we ask ourselves, well, what is sine of n 2 pi? Well, let's remind ourselves what n is here. N is simply a random integer, because the way we expand our series, a1, a2, a3, so n is an integer. And when you have an integer multiplied by 2 pi for any sine of this entire thing evaluates to 0, simply because n is an integer. So this means that this integral here, the sum of the integrals here, is equal to 0. Then we ask ourselves, well, what is this integral sine bn sine of nx dx equal to? Using the same logic, we realize that if we pull bn outside of the integral and the sum, and we ask ourselves what the integral 0 to 2 pi sine of nx dx is, it equals 0 again. So then these two terms sum to 0, and we have that term is equal to this. So then this is equal to 0. So then we have, finally, all things considered, integral 0 to 2 pi f of x dx is equal to our first term, a0, multiplied by 2 pi plus 0, which means that integral 0 to 2 pi f of x dx is equal to a0 2 pi. And that then implies that a0 is equal to 1 divided by 2 pi into the integral 0 to 2 pi of f of x dx. And let's erase our arrows here. So this is our final term for the first sum, for the first term in the Fourier series, and it'll take some work to evaluate an, so the nth term of the a sequence, so the an cos nx, and the bn for bn sine nx. So it'll take some work to evaluate these, but for now we will be satisfied with integrating for evaluating the first term in our Fourier series. And we will solve these terms in following videos. And this concludes our first video on the Fourier series. Thank you very much.